Welcome to Monad Student Zero, Extensible Effects, sometimes also called algebraic effects. My name is Stefan Sam, and I want to explain to you today how this thing works. I'm going to start with monads, see the limitations, and then go to extensible effects, how they work, how you can define your own, and some more add-ons. I'm Stefan Sam, freelancer, so was consultant for a couple of years, working in the field of data, machine learning and artificial intelligence. I'm the organizer of the Julia User Group Munich and very much interested in getting things into production, so professional best practices are always in my focus, but also probabilistic programming and functional programming more on the theory side, but you can actually use this quite a lot also, and best practices. Let's start simple. So what is a monad? A monad, as its key idea, is just an encapsulation of a computational context. So you have something you want to do behind the scenes, and the monad is simplifying this for you so that you don't have to think too much about it. Let's make it concrete, and I've chosen Context Manager as the example for today. So I've used this quite a lot in Python, so in other languages as well. We have a construction and a destruction, and Python with statements, and the context manager is there. It's called an enter and an exit routine. And this is super handy and can be used quite a lot. So we're going to implement this in Julia as well. Here we have a little type, my context manager, which just wraps a function and implementation. And we forward the call syntax to it, but just expecting a single argument, which we call the continuation. It's just another function, and we're going to see how it's working. So let's create our own context manager. And you see, we just wrap an anonymous function here. So we create this implementation, expecting this continuation. We first do some construction part. In this case, we could take quite a long to create the 42. And then we call our continuation with the value. So this is kind of the convention. This is how the outer world gets to know what we constructed. We get back the result, then do our destruction, and also forward the result back to the outer world. So this is our context, and we can actually already use it. And this is, we can just call it with a function, for example, with println. We see we get the construction and the 42, and then a destruction again. And what's really nice, and this mimics more the context manager you may know from Python, we can use Julia's do syntax. So we call the context now without an argument, and with do we can construct this anonymous function, which gets here. So we get our inner value, and we work with our inner value, and we print it to the outer world, and then we return it as well. So this is now a little bit different than before. So now we actually also have the return value, which is quite nice. Okay. So that's a nice context to work with. So we want to initialize and destroy it again. And working on it in a more mathematical term means that we have kind of a function f, and we want to apply it somehow to this 42, which, however, is encapsulated in our context. So first glance, this is quite difficult, but actually we can do it. And convention is that we store this logic in a higher order function, which is named map. So I'm not sure whether you expect this, but the simple map is the thing which we use. And now you see that it fits actually quite well. So we have our function f and our context, my context manager. And what we now do is we construct a new context manager, which encapsulates also this new computation. What do we do? So again, having this surrounding, we have just another context manager, but there's a continuation then. And now we have our context, we work within it, and we get the inner value, we apply our function f, and then finally we apply our new outer continuation to it. And that's it, everything works. So let's use this. So we have the map, we can apply something over it, and here's just, again, two versions with the do syntax or directly. And you see that we actually doubled our 42 to 84. So nice, that worked. Really great. So there's one step left. What we did so far is commonly named functor, and where we want to go is actually a monad. And here the left step is to combine multiple contexts. So let's assume we have kind of a function here, we call it f underscore context, and this creates another context manager given a value. So it again has another initialization and a destroy logic, now before and after, and it adds a random value here, 1111. And we can use our map and look what happens, but it's really not useful. So what you see, we have the other context manager, which is still not executed. However, we already run the destruction. So this definitely doesn't make sense. You don't want to do that. What you would like to do is that you merge both context managers together so that you have the initialization routine from the one and from the other run before this is actually used. And this merging together is sometimes also called join or flatten, and hence the function, the name is actually also taken from Scala, is named flatMap. And it's defined in a package of mine called type classes. There's this flatMap operation, and it applies, now it looks very similar to the map, but our function returns another context, another computational context itself. So what we do, we construct again our context manager, which gets the continuation. So this part is very same. And we again work within our existing context, we get the inner value, and we call our function on the inner value. So what we now get is another context, an inner context, and we somehow need to combine this with the continuation. And luckily, the context really knows how to work with the continuation. We just need to call it with it. And that's it. This actually works quite nicely. So if we now apply this flat map, we actually do it the correct way and see all the things which we wanted. So that's really nice. Having map and flat map, we get a lot for free. And type classes implements a macro called syntax flat map, and you see it here on the left, like you would use it, and on the right, what it translates to. So this, you just use normal assignment with an equal sign, and this will translate to a flat map on the right. And if you have multiple of these equal signs, there are multiple nested flat maps. So you don't want to write the right side. You really will enjoy the left simplification. So that's really nice, and works. And the syntax is actually more powerful. So a normal equal sign now works in this computational context. Sometimes you also want to do some normal transformations. And there's an extra macro called pure, with which you can insert other normal computations. And you see it on the right side what it translates to, and they will just be inserted at the right part. And you now here in the more complex example, you see that the first things are always translated to flat maps, and the very last call will be translated to a normal map. So this is really, really handy and works quite well. Works really well. So that was the first part. Let's come to the second big thing. So what are the limitations of this? Why are we going to look at extensible effects? And the limitation is that these monads don't compose well. So we have here one or two monads which are actually supported by the picture of the box. On the one side a vector. So we can also use syntax flatMap on vectors, and you see it just works like two for loops, like a nested for loop. We combine all the combinations together. And on the right side, we again have our context manager, but now we use actually context manager implemented in type classes. So there we have a bit more support and don't need to implement it ourselves. But it's again the same. Now we have another function called create context, and they work as we know them. So now we want to compose them. And actually the one way works and the other not. So if we first have the vector and then the context manager, we get something out. So what happens here? The key thing is that the context manager is converted, or it tries to convert the context manager to the vector. And this is actually supported, but for convenience, the implementation is that the context manager is run. And hence you see the output here without the println statement, which we always had, because the context manager is then run with the identity function. And so we get our values and we execute everything that indeed correctly, so that the values are kind of finished, and this should work usually. On the other side, we have the other way around. They have the context manager and the vector, and now the conversion is the other way around as well. So the vector is tried to be converted to a context manager, and this is not possible in no way, because the vector is like representing indeterminism, has either 0 or 1 or multiple values, but a context manager always has one value wrapped into initialization and exit. So this doesn't fit. We cannot convert multiple or 0 things to one thing. It's definitely not possible, and hence this must fail. Okay, so there's a solution to it, and the solution is called extensible effects. So this composing of monads, there have been actually a couple of solutions, and the most well-known is one part is extensible effects, and the other is called the monad transformers. Just to mention them, they would be difficult to port to Julia, and they don't compose well. So the extensible effects is really the preferred solution, and they fit also very naturally to Julia. So I followed the implementation, came from a paper, and that's also Haskell implementation, also Scala implementation. So let's see that it works. So this is how you would use the extensible effects, or one way to use it. And we have, again, we can use the same thing, create our context manager is supported, we have also vector which is supported, and we can run it. So this thing will now give us a context manager. And as you see, if we put it the other way around, we also get a context manager. So we don't have any fancy conversion implicitly, which is just there for convenience, but everything is kind of really well defined and works nicely together. And it's no black magic, it's really the intended way. So we have this way, and things really work like we wanted to have it. Let's take a look how this works. So first part is the syntax, again, syntax effect, and no outrun. And this part is again translated here to the right. So this thing you already see, the flat map and map. So this part that equal signs are translated, this is the very same. What is new here is that we wrap our values into an effect. So we have extensible effect, and let's see what this does. And it really just wraps it into this internal type representation called f. And this f, so everything is wrapped into it, and it's just wrapped for later lazy execution. So at this step, we don't do anything, we just build up an internal representation, and that's it. Let's take a look what it means concretely. So this is the f type, and it just has two things. That has a value, an effectful value, so either a vector or a context manager, for example, and it also has the continuation, so everything which should be done on this value which is captured in it. And the key thing now for f is that this continuation will return another f. So we continue with something, and then we get another of this meta representation of this f, and then things continue again. So this is the recursive cycle. Having this meta representation, this syntax representation if you want, we can actually run it. And let's take a look before and after what happens when we run it. So we run first our vector. So before we can see the value and we see the continuation. So the value is our context manager, and the continuation is an internal type called continuation, which is like a function, but a function broken down into multiple functions, which then finally should be composed, but for performance optimization, they are just stored independently. So if we run our vector handler, some things change. So the value actually is exactly the same, doesn't change at all. However, the continuation will change. And what happens is that in this continuation, we now change that every vector type will actually be executed. So this is kind of remembering that our vector is actually run. And this will recursively apply to each continuation until every vector then finally is handled. So this means that in this continuation, there's kind of no vector any longer, but everything will be handled as soon as a vector is seen. Okay, let's go to the more complex part where a vector is seen. So this is now the key part, and if you understood this, you understood the key idea. Okay, let's take it the other way around. We start with a vector and then have our context. So A is now here the simple vector, and then the second part is the context manager. Okay, nice. We see now this is a quite complex continuation, and as said, the continuation is broken down to several functions, and we can just print the length of it to see that it changed. So we run the vector again now, and we now see that actually a couple of things changed. So the value is no longer the vector, but now the context manager. So this is because the vector was actually handled. And the continuation also changed. So we have the same as before, that now it remembers that the vector handler needs to be run. So that's the first part, hence this change. But there's another part. Because the vector was handled, was executed, there's kind of a special thing happening, because it was actually applying this continuation one time to the 100 and another time to the 200. So remember, the vector is just kind of an indeterminism. It really tries all combinations of things which come in. And yeah, so the key thing here is now that, okay, we have multiple threads which go, but finally our F-type only has one continuation. So that's really the thing going on here. We somehow need to combine these multiple things into one thing. And this is what I want to explain to you on the next slide. So what happens in detail if we handle this vector? So if you understood this slide, you really got something. So let's start with the vector. We have a 100 and a 200. And that's, yeah, so our starting point. So now for each of this element, we run our continuation. And remember, this continuation always returns an effect. We can take a look at it. So we define our continuation, and we can use our syntax, and that's nice. And we map it onto our vector, so yeah, perfect. So third step is now to realize that we now have really one effect encapsulating the result for the 100, if we put 100 into it, and we have a second effect which encapsulates the result for the 200 part. So we can just store this to two separate variables, and you can check they are really effect values. Okay, so now last part is that we somehow need to combine these together into one. And yeah, the key idea is that we can actually do the same like we did with our context manager. So this F-type is actually a monad. So the implementation is provided to you by extensible effects. And yeah, because it's a monad, you don't have to care so much about the computation context, but you can just use it. And so we use our syntax flat map, which you definitely remember from the beginning. And we just deal with these F values like they would be an arbitrary monad. We extract the value from the 100 result, and we extract the value from the 200 result, and finally we put them together into our array. And that's it. So now we combine these two strengths into one final effect, and this, by background magic, combined the continuations into one final continuation. The precise definition is a bit different. We're going to see that. This because a vector can be of arbitrary length, and now here we assume for simplicity that's just two elements. But the key idea is really the same. Yeah? So we use the monad feature of F, and everything works out. So I hope you got this slide. This is really kind of the key idea behind it. Okay, almost there at the end. So let's define our own effects, and there we also see kind of a little bit more details. So what's the interface for your effects? The interface is that we have a function called fApplies, which checks whether your handler actually applies to the given monad. We have a pure function, which which wraps the given value into your monad. So here we have just a simple vector of one element. Yeah, it's very, very simple. And we have a final function. This is the key function, the flat map function. And this gets a continuation and needs to apply to a vector. However, there are a bit more details to what this flat map needs to provide, but easiest is to see the generic definition of them. So it turns out that the pure can be just implemented by default by type classes.pure. So you can define this also kind of for yourself, but in most cases this will actually be enough. So it's just a simpler semantics. And now the second part is really interesting. So the flat map, what is done here, can be completely specified by falling back to type classes. So we have a monad A, and we have this continuation. First thing we need to do is we need to map this continuation over our monad. So this will actually return something, A of, or this effect type of the same monad. So this is key, and this is guaranteed by the framework. So Extensible Effects makes sure that this is really the structure you will get. And what we finally want to return, however, is something different. This is namely an effect of our monad. So this is our goal. And we can come there, and the first thing we apply is the flip types, which is actually, which is exactly for this, that we have, we switch the outer two layers. And then we have an f of an a, and we need to combine these two inner a's. For that we need to work within our f, so we make a map, and then within our f we flatten out these two a's to 1, and this is it. So this is the default implementation of the flat map, and this is actually the real implementation for vector which is used. Okay, so some little extra details. So flatten just wraps type class flat map, so that's the thing which we actually need to define. And the flip types function can sometimes be easy, sometimes be hard to define. And if you type iterates, and if it has several values, then it needs also to combine. In addition, there's actually a default implementation which you can use. And yeah, so this is kind of the concrete implementations for vector. So we have the f applies. You always need to provide this explicitly, which handles what. Then we have this map. We just map over our vector. We have the iterate, which is the standard definition for vector. We have the pure definition, just wrapping it into a value again. And we have our type class as flat map now, not the f flat map, which is just flattening out these two vectors. All standard, and combining two vectors is also very, very simple. So this is the recommended set of functions which you need to provide. And yeah, if possible. And if not possible, you can always also define a flat map. Just take a look at the tests and at the documentation to understand what you can do there. And if this still doesn't work, probably your handler needs some additional information and you can define custom handlers. Okay, last part, let's go on to some additions, some extra things. Extensible effects come with a function which is called autorun, and this is actually applied by default, so you don't need to call every handler, but most handlers can be autorun. So you see here, it's really nice and simple. You just use syntax f, and this replaces kind of your syntax flat map, and it will just work. Context manager is also interesting to have an extra remark. Concretely, the context manager assumes that the continuation will actually finish its computation and then things are destroyed again. However, with this effect system, computations may be held on for later, so they may be lazy and things are actually not run. So we need to make sure context manager are handled last. And this is actually ensured by the system, so you can't make it wrong. But that's a specific thing. And there's actually a second handler for context manager, which is called context manager combined handler. And this is actually interesting because it changes the order of execution. So take a look at these two examples. And the second one, which uses the context manager combined handler combined with a vector, really has more efficient execution, so that more memory efficient things are initialized and destroyed the right time when they are needed. Okay, so, and then there are also a couple of other effects you can use. So for data type basic is option, try either identity const context manager, like a couple of standards. Type classes comes with callable, where you can wrap your functions, iterables, where you can wrap your iterables, your iterations, state and writer also, for example, and from base, vector is supported, task and future. Okay, let's wrap it up. So what you got to know is that monads are actually just an encapsulation of a computational context to simplify your life. We saw the context manager to make it simple, and we also have this extensible effects which uses the same semantics. If you have provided the map and the flat map, you get even nice syntax which you can use right away and makes things really simple. However, monads do not compose well, and this is where extensible effects comes in. They do so, they compose well by defining a meta monad, which is called f, and this stores just everything for lazy execution later on. Then we have on the other side our handlers, which define how these monads effects are actually then run. Thanks to the autorun feature, which I implemented for you, you don't need to bother so much about the handlers. So actually, in most cases, it will just run automatically for you. But in some cases, they are really important. We saw one, there's this context manager, which actually already has two different handlers because they lead to different execution orders, which may be interesting for you. Many monads are implemented for you. You can just take a look at the documentation and tests, either to work with it or just to understand how things are happening. Thank you for your attention. It was really nice. Take a look at the repositories, extensible effects, type classes, and data types basics. Take a look at the code, test, the docs, and don't hesitate to just also ask for questions. You're always welcome to reach out. Thanks so much and enjoy the conference.